So thank you so much, Marina, for that introduction. And also, first of all, I would like to acknowledge the traditional custodians of the land where I talk from today, the Watamotagal clan of the Darug Nation, and pay my respects to their elders past, present and future. So I'd like to say thank you to the GSA for the opportunity to share some of the work that we're doing, find out about our rich volcanic history in Australia. So I hope to show today the benefits of a holistic approach to understanding volcanic and magmatic systems and their impacts, particularly highlighting the advancement in understanding that's brought through integration of Indigenous knowledge with volcanological, mineralogical and geochronological data. And you are struggle to get through those three. So obviously this is focused on Australia, but the importance and the significance of this work today is relevant for all basaltic intraplate volcanic fields. So these are those that are located in the middle of tectonic plates. They occur on every continent and represent some of the least well understood volcanic systems on Earth. And they're often areas with large populations of people. For example, the Auckland volcanic fields obviously hosts about a third of New Zealand's population, and Mexico City is built upon one of the Mexican intraplate volcanic fields. So research on Australian systems not only improve our understanding of our systems close to home, but also has global relevance. So you probably had your own thoughts when you read the title today, ranging from, is this a joke, to, I'm not sure I'd really ever thought about that. So you're not alone really in your range of thoughts and opinions on the topic of future activity, volcanic activity in Australia. I just wanted to share with you what 5 Australian academic geoscientists said when they were questioned by the media, and arrange these from left, where it's almost a joke and there's little consideration of active fields, across to the right, where you can see we've got signals of imminent eruptions. So some of these quotes, so one on the left, I've not identified people by name, but I've just indicated the institution that these quotes came from that were highlighted in the media. So we range from, there are no active volcanoes on the Australian continent. However, if you're a time traveler and land in Australia in 5,000 years, you better watch out. 2, at the other side, I guess, of the extreme of thought and opinion, an eruption could hit Melbourne at any moment. In terms of Melbourne and Auckland, there's every chance another volcano could blow. You can see lava flowing down Burke Street. So you can see, even amongst the geoscience community, we have a range of opinion on this topic of, does Australia have any active volcanic areas, and when will the next eruption be? So there will be a little bit of audience participation today. So before we go any further, I'd just like to take a step back and just see in a poll what you all think really about the number of people that would be living on Earth within 100 kilometers of an active volcano. So if I can manage to pull this poll, let's just do this one. Okay, so hopefully you can now see the poll. So if you just indicate, so you've got options, 20 million, 80 million, 200 million, or 800 million. And let's see what everybody thinks. It's still moving around a little bit, so I'll just give everyone a few more seconds. Are we almost there? Okay, we're almost there. All right, so I'll share the poll now. So we can see it was pretty even. We've got, can you see that now? Yeah, it says you can see it. So we've got the highest vote for 200 million people living around within 100 kilometers of an active volcano. So I'll just stop sharing this and we'll go find out the answer. So the actual answer is over 800 million people in the world that live within 100 kilometers of an active volcano. So I'm not just trying to justify my own job here, but with an increasing global population and pressure on land, more and more people are living close to active volcanoes. So we really need to understand what causes their eruptions, what triggers eruptions, how they operate and what's going on below ground and how long. Yes, the precursors to things that are going on underground that we can use for volcanological, mineralogical, geochemical information to understand better about how they work. And from this, we can see that there's over 29 million people living within 10 kilometers of the vent. So in some cases, those people are probably living on the lower slopes of volcanoes, so very much at risk from volcanic activity. And you can see there Indonesia has the highest amount. It's got a dense population and it's got over 129 active volcanoes. So there's a lot of people in Indonesia that are at risk from volcanic activity, from volcanic hazards. So the idea for that poll as well was just to get you thinking, I don't know if anybody wondered, was what does active mean? So when we think of an active volcano, we might think of, these images in our minds of lava flows, of flying volcanic bombs, of plumes coming out of volcanoes. So there will be at least 20, as I speak, 20 volcanoes probably erupting, and anywhere between 50 and 70 volcanoes erupting in a year. And so no doubt they are active. And you can see from the picture there of Big Ben on Heard Island, that you can see at the top there of Mawson Peak, you can see there's a plume being emitted. So you would definitely class this volcano as active. But because the dormant intervals between major eruptions as individual volcanoes may last hundreds to tens of thousands of years, this dwarfs the relatively short historical record in many regions. So it's misleading to restrict the use of an active volcano to a recorded human memory. And as an example of this, before Mount Pinatubo erupted in the Philippines in 1991, the volcano had been sleeping for over 100 years with no historical records of past eruption. So no one had been keeping a close eye on it. And that eruption was the largest of the 20th century and produced a 2.5 kilometer wide caldera and lowered the summit of the volcano by 300 meters. And going to the more other extreme of these big supervolcanic eruptions, recurrence intervals at those, such as Yellowstone, it's had 3 eruptions over the last 2.1 million years, giving a recurrence interval there of 600,000 to 800,000 years. So what do we classify as active? Well, the general consensus and one used by the Global Volcanism Programme is to consider an active volcano as one that has erupted during the Holocene, so approximately in the last 10,000 years, and that has the potential to erupt again in the future. We also have to take into account the spatial arrangements of vents. So if you're in a subduction zone environment where you might have a nice typical, stereotypical conical volcano, largely that volcano will erupt from that single vent and from the top of the volcano. But it can get more complicated than that. So we can get fields of volcanoes, so over quite wide areas, over hundreds of kilometers. So in that case, it's possible to define the actual area or the general region as active, but each individual vent or volcano within that region would be considered extinct and unlikely to erupt again. So you can see that it's not so simple to decide what active means, but we all need to come to some sort of consensus if we're going to communicate clearly and effectively about volcanic hazards and risk. So coming back to Australia, so since the demise of the dinosaurs, we've had a lot of activity, so in the Cenozoic down the eastern coast of Australia. And do we have any young volcanism that would be less than 10,000 years? So the answer is yes. So I've highlighted here in the 2 blue circles. So in the northeast Queensland, we have the Kinrara volcanic eruption that's dated at 7,000 years, -2. And then in the southeast of the country, we have Mount Gambier and Mount Schenk that are both thought to be around 5,000 years old. So we do have young volcanism that then could be considered might have future activity. We also know that a lot of these fields and a lot of the activity in Australia can span tens of millions of years. So we can have quite long periods of volcanic activity. So the frequency of eruptions can be quite spread out in time, can last for millions of years, but we have got some recent volcanic eruptions. And the other thing is we've got some more evidence that there could be geophysical anomalies, at least where studies have been done in the Newer Volcanics province in Southeast Australia, where they think they can see that there are geophysical anomalies that might represent some intruded magmatic sills that still have proportions of melt remaining from low velocity zones that also correlate to the top of a prominent low resistivity zone. So where might we see a future eruption? Well, my best estimate would be in either one of these areas where we've got the most recent volcanic activity. So that leads us on to how much warning time might we have. So we've not had an eruption since the availability of seismic monitoring to seismic monitor. So it's not really known what's going to happen before a future eruption. But there are ways we can gain insight into how much warning time we might be provided. And we can do this in a number of ways. So one is trying to look at, trying to understand past eruptions, how magma has moved from the source to the surface. So we're going to look at a few examples of that. And we can also look at eruption events and impacts. So we can look at eruption sequences from the volcanological records, so stratigraphy. We can date some of those layers. We can try and work out periods of activity in between. And then we can also look at eyewitness accounts or monitoring of past events. So in Australia, the last eruptions occurred around 5,000 years ago. So humans have been living in Australia for probably at least the last 65,000 years, and it's likely that they've witnessed about 13 or so eruptions during that time. So through oral histories and knowledge of some of the more recent volcanic events, we can possibly extract some information about what those events look like and what the warning signs might have been, and how quickly things progress during eruptions from the oral histories and stories that have been recorded. So first we'll have a look at what mantle xenoliths can tell us. So mantle xenoliths are these fragments of rock from the Earth's mantle that get brought up by magma on its way to the surface. So this is a collection of xenoliths from the Newer Volcanic Province and the Atherton Volcanic Province, so in the southeast and northeast of Australia. And it's a study that Tom England undertook as an undergraduate project, and he's now just started a Master of Research with us here. So he looked at over 100 xenoliths, both from the field photos that we took and also from ones that we brought back. But I do have to acknowledge there is some sampling bias because we picked a lot of the larger ones to come home with us. But yeah, we had all the field volcanoes. And what he saw is that there's an average size of about 10 centimeters from what we got, and our maximum size of xenolith was about 25 centimeters in diameter. There are some volcanic treats throughout the talk when you look for these QR codes. So what these QR codes are models, so 3D virtual models of some of these xenoliths. So if you want to take pictures or have a look, and once this talk's recorded, you can access them through that too. But we've got these interactive 3D models that you can rotate, zoom in on and have a look at. So some of these xenoliths have been immortalized in virtual sense. So please feel free to take pictures of the slides where you see the QR codes throughout the talk. So this brings us to the second poll and the final poll of the talk. And the question really is, I'm just wondering what you think, how fast would a 25 centimeter mantle xenolith? So I've got one that's about, just for scale, if I can lift it up, I don't know if you can see this. This one looks like it's about 12. I don't know if you can see this one okay. So if we've got one that's 25 centimeters in diameter, how fast do you think it could travel from its source? So we're assuming here something below the crust mantle boundary, so we're estimating maybe 50 kilometers depth to the surface. So bearing in mind that these, I'm just going to start the poll. I'll keep talking. Okay, so you should see that now. So you have to bear in mind, so these bits or fragments of the mantle are dense, and to move them, you have to move pretty fast. So let's see what everybody thinks. I'm getting a range of answers in here. So the thing is, if they're dense and they're heavy, they want to settle it and sink out. So let's see I think we've got some sort of final. Okay, I'm going to share it now if everybody's got their votes in. Okay, so 2 days is quite even between 2 hours, kind of to 2 weeks. But obviously people realize that we're going to need to move these things pretty fast. So just share those results with you there. So, and we'll find out now. So there is a way we can have an estimate of what we think from the size of the xenolith that we see. There are some assumptions to be made, but we can see how fast this might be. going to close this. So there are some assumptions to be made, but we can have a guess at how much time it would take to basically overcome the settling rate. So your magma ascent speed has got to be pretty fast to overcome this dense fragment of the mantle settling back down in the magma as it's moving towards the surface. So what we need to overcome is this yield strength of the magma, and that yield strength would increase if we increase the crystal content. So what we're going to do for just the case of simplicity is just assume that we have a purely viscous fluid here, so something just like honey without any crystals in. And what we're going to do is move from the source, in which case we're fixing it at 50 kilometers, so somewhere in the upper mantle, pick a fragment of that rock and bring it up with a magma. So what we're going to do is see how fast that would need to be to carry that without it sinking, based on the maximum size that we've observed from Tom's work on measuring the sizes and shapes of the xenoliths. So what we have along this x-axis is the xenolith radius. So we've been seeing up to 25 centimeter in diameter, so about 12.5 radius. And then from that, we can have a look at the settling velocity that comes through. And we know then that's our minimum ascent rate. So we have to move faster than that, the magma, to the surface to avoid the xenolith sinking. So have a look. So you can see here, this is our average size, but there was a little bit of bias in what we brought back with us as well. But the maximum one is probably the important one. And what we can do is if we take a xenolith of 25 centimeters, so one of our maximum ones, and we move it to the surface, we can see that it takes about 50 hours to get to the surface. So in 2 days, so the speed that you would have to move, you'd have to get it there in extremely fast time frames. So we're just talking in a couple of days to be able to move this without it sinking down or settling out. So I guess it's one thing to use equations and assumptions to try and work this out from a maximum xenolith side. And obviously that assumes there's spherical xenoliths, and we can see clearly from when we've been doing the study that they're not all spherical in shape. We have a lot of more angular type elongate xenoliths, which then would probably settle more slowly. But what we can do then is look towards what we actually see in the rocks in Australia. So by having a look at the crystals within the rock, we can get a really good view about the history and the processes that have been going on in the magma on this journey to the surface. So in the same way that tree rings would record, you chop a tree, you look at the tree rings would record the rainfall, the temperature, so the environment that tree was growing in. Volcanic crystals within a rock can do the same thing, so that we can see the history of growth, and they recorded their environment, the pressures and temperatures, the water contents, the oxygen fugacity. They recorded all of this information as they were growing. And a lot of these crystals then, so this is actually a plagioclase crystal. I've just used an example from Indonesia, so not from Australia. But we can see similar things in Australian crystals. So this is one from Mount Shank. This is a clinopyroxene, a nice euhedral, so nice outline clinopyroxene. And you can see we've got these rings again. We've also got some sector zoning in these crystals, which is why you've got darker bits at the ends. But we can see these rings, this oscillatory zoning, which probably represents changes in composition during growth. So we have this history recorded in these crystals that we can access. And just to note that the scale of this is about 60 microns across here, which is about the thickness of a human hair. So some of these crystals are extremely small, but we can get really good information about what's going on beneath volcanoes from them. So I just had to share some of these pictures. So these are pictures from mostly from Mount Shank, but also from the Atherton Volcanic Province. And you can see the incredible range of textures and crystal shapes or mineral morphologies that we can see within the rocks in Australia. And all of this can yield information about the magmatic processes of ascent. So especially where we've got these clinopyroxene, you can see these little dendritic, we've got feather-like structures, we've got skeletal olivines, with dendritic overgrowths, we've got little euhedral, but all of this information, when we put it together, can tell us all about the ascent pathways that these rocks were going. So to get dendritic type and skeletal, we know that we're cooling below the liquidus for that mineral, probably quite significantly, like tens of degrees. And it's not growing in equilibrium conditions. So we can use all of this information from the textures that we see from these incredible shapes that we get from the crystals to learn something about the ascent of how these things get to the surface. But we can also do something else with the textures and the zoning patterns of the chemistry within the minerals that we see. So here's an olivine from Mount Schank, and this is a backscattered electron image. So each change in the grey colour represents a change in composition. And if we imagine that we started off with an olivine, so this is an example olivine here at the bottom in the green, dark green, there's all the same composition, it grew, but then it encountered a magma or melt with different composition and it grew a rim. And then over time, that tried to equilibrate through diffusion. So you get this relaxing of this big jump in the step. So what we can do with diffusion chronology, just get to the next one, is we can take chemical profiles across the crystals, like here, and then what you do with some assumptions about how fast those elements diffuse in those minerals, about the temperature, about your starting compositions, you can work out then based on the slope, so how steep that line is between those two jumps in composition, whether it's steep or whether it's quite gentle, that can give you then an indication of the time scale of the process. So how long since that event happened before eruption, and this process is recorded for high temperature. So at low temperature, once you get below a certain temperature, it kind of just cuts off. So we can get a lot of information from these crystals about ascent. So Rosa Dodonna's postdoc for the last year and a bit now, she's been looking at mostly focused on Mount Noorat and Mount Laura in Victoria, so in the New Volcanic Province. So we've been taking thin sections or polished sections of the rock. Here's a picture in cross-polarized light, and just zooming in on this little crystal here, you can see that it's got, in cross-polarized light, you can see that there's a different color at the outside representing difference in composition. And what you see when you look at these rocks, especially the ones from Mount Noorat, is that most of the olivine in these rocks are not in equilibrium with the melt. So these are xenocrysts that have been picked up from the mantle, broken down, and then carried by the magma to the surface. So this crystal started off in equilibrium with the mantle in the upper mantle, and then it got plucked out and it's got broken down and plucked out by the melt, and then it's not happy in that new environment chemically, so it starts to grow a rim, and then over time that can diffuse. So here's another one of these backscattered electron images from the scanning electron microscope. So you can see here's this rim in this light color, and then this is the original core composition that was in equilibrium with the mantle conditions, and then it grew this rim. And how slopes this boundary is between the rim and the core is what we can use to work out the time scale of that interaction. So when it got exposed to the melt before it was erupted at the surface. So if we take this green line here, this is the magnesium number. So this is our magnesium content of this olivine. You can see that we do have this nice profile. So here's our interior area, and then towards the rim, we get the slope, and then it goes lower at the rim. So this kind of normal zoning profile. And what Rose has done is she's then used temperature estimations, oxygen fugacity estimations, diffusion coefficients, and she's also looked at some EBSD to get the orientation of the grain, because the diffusion goes faster in different directions in the grain, and to work out some timescales and see how that compares to the analytical estimate from the settling rate of the size of the xenolith that we find also at Noorat. So from that, it looks like the timescales are quite comparable, and we're looking at a scale of hours to days for the timescale, diffusion timescales, which are comparable to this kind of 2-day rough estimate that we've got from doing the analytical modeling. So we have, from this work, an estimate of quite fast movement of magma from deep in the earth to the surface overall. And so the warning times associated with that, if you think this is kind of a time frame of mantle to surface, you know, warning times, we might pick up earthquakes at shallower levels when the crust is more brittle. So you're looking at these are maximum warning timeframes of just the order of probably days. So is there any evidence from oral or previous witnesses of eruption that can kind of support or indicate what the warning times have been like? So this is where Indigenous knowledge of past volcanic events in Australia is extremely valuable. So eruptions have been happening here over the last 65,000 years while people have been living here. And Tower Hill, which erupted around 37,000 years ago, when that erupted, it buried stone tools, implements, and Aboriginal implements. So we know for sure that at least when Tower Hill was erupting 37,000 years ago, there were already humans in the south of Australia, southeast of Australia, living and experiencing and witnessing some of these eruptions. And it's by utilizing or interpreting the oral stories recorded as memories of eyewitness accounts. And obviously there are some factors that obviously play a role in limitations of what you can get out of oral traditions, but the value that they can bring to understanding both pre-eruption events, so what they can tell us about warning signs and signals, eruption, so how the eruption progressed, what the events were throughout the eruption, and also timing. So sometimes the material that we have at volcanoes is too weathered to date, or the dating uncertainties are really significant, so we can't get too much from that. So Indigenous knowledge can also help us understand the relative timing of events. And that's what I'd like to go through on this first one. So Mount Gambier and Mount Shank, both thought to have occurred around 5,000 years ago, last eruptions in Australia. But when you actually compile the ages produced or the dates of these eruptions, there's a lot of variability, and also there's not a good consistency between which one came first. So the paleomagnetic data defines that there's about 300 years between the eruptions of Mount Gambier and Mount Shank, but it can't tell you which one came first or which one came second. So the oral knowledge actually can indicate the relative timing, because there's a story of a great or giant ancestor to the Volcanic people called Cratebill, who with his wife and 2 sons wanted to find somewhere to live free from the fear of an evil spirit. So they settled on Mount Muirhead, where they made an oven. But then one night after making their oven and going to bed, they were woken up by the noise of a bird called the bullin. And it was the fear of the evil spirit that they fled to Mount Shank, where they thought they would be safe from the evil spirit. But then it happened again one night when the oven was empty, the voice of the bullin occurred again. So they got up and went further inland, believing that the evil spirit couldn't live far from the sea. And this time settled at Mount Gambier, where they stayed for a long time. And as usual, made their oven, but then one day the water came up from the bottom and put out their fire. So they made more ovens, but each of the 4 ovens they made, the water came up. And the last home was a cave in the side of the peak. And this was a story recorded by a missionary lady in the 1880, which she published in 1880. So from this, if we extract the information, obviously we've got some reference to the volcanic landforms that were left, whether the oven was empty or whether it was closed. So whether basically there's a crater or whether it's a mound. But what it can tell us or indicates is the relative timing of events. So Mount Muirhead was older than Mount Shank, and then Mount Shank was older than Mount Gambier. So we can understand something about relative timing that can go beyond what the dating or current age ranges that we've got from those volcanic centers. And then just the other story I'd like to highlight at the moment is one from Lake Eacham in Atherton Volcanic Province up in northeast Queensland. So there's an Aboriginal oral tradition recorded on there in two different dialects or local languages, how 2 newly initiated men broke taboo and so angered the rainbow serpent. And the point is here from the story is that everything happened pretty fast. So at one point there was an old man that went to look for food, and he told the young newly initiated men to stay put. But then he realized while he was out looking for food, it got dark. So he knew that they'd be in trouble. So he went back to camp. And when he went back to camp, there was a cloud in the sky, there was a wind blowing, and there was water rushing up and engulfing everything. He tried to hit the land and tried to put this out, tried to send it away. But all the animals came running, partly blown by the wind. Then the water came up and the people were gone. So there was literally from that, I extract that there was very little time to respond to what was happening, that these were quite sudden and dramatic events and that people didn't have time to escape. So these is consistent with a phreatomagmatic eruption that are quite explosive. And that's why we have the lake there. It's a maar, so it's where groundwater in the system, magmas come towards the surface, interact with that groundwater and cause these highly explosive phreatomagmatic volcanic events, which are, rapid eruptions, very powerful. So the other part of the story that's just really interesting to highlight is that in the story is highlighted at the time that the environment when this happened was open scrub. Now there was a pollen analysis study, which in the 1970s, which indicated that the present rainforest biota was less than 7,600 years old. So this is consistent with the fact that before that time, there was probably a different biota in the area, and that it's consistent with open scrub that's in the story. And the dating from the lake sediments provides a minimum age for Lake Eacham of about 9.1 thousand years old. So the question is, how prepared are we? If these events can happen quite fast, if we might only have a few days notice of an event, how prepared are we? Well, Joshua van Atterloo and Ray Cass and others did some modelling to work out what the size of the last eruption was at Mount Gambier. So we can compare and measure the size of individual volcanic eruptions using a volcanic explosivity index. And it usually uses the amount of material ejected along with an estimate of the plume height. And the calculations for Mount Gambier suggested that this had a volcanic explosivity index of 4. So the scale currently runs from 0 to 8, where 0 would be something you could walk away from, like a gentle, effusive, oozing lava flow in Hawaii, and 8 would be a supervolcanic eruption. So 4 is it's quite moderate. And just to put this in comparison, the 2010 eruption of Eyjafjallajökull in Iceland was also a VEI4 and phreatomagmatic, which was what the Mount Gambier eruption was. So what Ray and others did in 2017 was superimpose the ash cloud from the Eyjafjallajökull eruption on top of Mount Gambier with prevailing wind conditions, just as an example to show how far the ash could travel from an eruption of that magnitude. So you can see it's quite significant on here, and it reaches all the way across to Auckland. So based, I guess, on this, that we may not have much warning time if there is future, even though it could be thousands of years between eruptions. And the fact that we could have a significant eruption if it did occur in an area where there was groundwater and it led to phreatomagmatic explosive eruptions, led us to wonder how prepared are Australians for both volcanic activity in Australia and also from outside Australia. So at the end of November in 2019, we launched a public survey of about 38 questions, but so we launched it in November 2019, then in December there was the tragedy at White Island at Macquarie, then we had bushfires, and then we had coronavirus. It never seemed like a very good time to really push a survey on volcanic hazards to the Australian public. So we took it very slowly last year, and we're just starting off again now. But we've got 195 responses to date. So I just wanted to share some of the opinions that we have from the public. So when we asked the public if they agreed or not that there are parts of Australia that are volcanically active, there was quite a range in answer. Now, we did capture, what everybody's interest was in and what they thought their knowledge was, how well they thought they knew about, natural hazards, volcanic activity. We also captured, what level, if they'd done HSC, Earth and Environmental Science, and also what their highest qualification was. So we know we have some dominance of people with a strong background in earth science and then people that definitely don't have any background or any prior knowledge. So I need to interrogate the results very closely based on that background, education and knowledge that people had coming into the survey. But what you can see is that a lot of people didn't really know. So neither agree or disagree was 30%. So a third of people didn't really know. 23% somewhat agreed, 28% somewhat disagreed, and it was similar percentages of around 10% for whether they strongly agreed or strongly disagreed. So a lot of difference in opinion there. But over a third were not sure when the last eruption in mainland Australia occurred. And there were also a lot of people, the next bracket down, that was for the most of the population did know when that eruption occurred, and said within the last 100,000 years, between 1,000 and 100,000 years. We also asked, we tried to just cover people's, this was before, we wrote this before the pandemic, and pandemic wasn't actually one of the questions that we asked people if they were concerned about that to their well-being or livelihood, a pandemic. So that isn't included, but what we asked people was how concerned they were about the risk to different hazards to their well-being or livelihood. So the top diagram there shows things that people were not all concerned with, and then the bottom shows people that they were extremely concerned. And it's as you would expect, really, for Australia, that these events, these natural hazards or events that happen infrequently and have not really occurred in, affected Australians that recently. I guess the Newcastle earthquake would have been the last major earthquake to affect Australia, and that was about 30 years ago, or just over 30 years ago. So you can see that earthquakes, volcanic activity, cyclones, tsunamis, they're not at all concerned about. And things that have been more prevalent in recent years, bushfires, drought, climate change, along with housing affordability and education affordability, are more on the minds of the Australian public. But what's interesting is that even though they recognised that volcanic activity was not something they were concerned at all about, 80% agreed or strongly agreed that Australia could be impacted from volcanic activity in other countries. And these were answers that were both, before and after the White Island tragedy. Only 4% agreed that Australia is prepared for dealing with volcanic eruptions, and only 6% were aware of any preparedness emergency management plans or warning systems, such as the volcanic ash advisory centres in Australia for volcanic hazards. So a few things, a few interesting points there, and once we've got, I'm hoping for probably up to 400 survey responses before we close the survey to get a good sample of the population. We still don't have really enough people from the Northern Territory, from Western Australia, from South Australia, so we're working, and Tasmania. So we're working hard to try and increase respondents in those areas. So just to summarise what we've gone through today, where do we think that there might be future volcanic activity in Australia? So I guess based on the young ages of volcanism, the most recent ages, it would be my guess that it'd be Southeast Australia, so around the New Volcanic Province, or up in Northeast Queensland. When? We don't know. We don't have any indication yet when it might happen, whether it would be in a short time frame, whether it be in thousands of years, but I personally consider that it will happen again based on the longevity of these fields and the young ages of some of the volcanoes in these areas. And how much warning time? So we've seen from both the Indigenous oral histories combined with the mineralogical and the xenolith information that these events, when they're at the surface, they happen fast and there might not be much time to respond, but we could only have possibly hours to days, maybe weeks if we're lucky, of notice of a forthcoming event. And how prepared are we? Well, there's very limited public communication and knowledge around volcanic hazards and risk, both from inside and outside Australia at present, and also disagreement within the geoscientific community who are giving conflicting messages through the media to the public about Australia's volcanic hazards and risks. And then this is, I just wanted to show you this 3D model that we've been working with. So with Tom Raimundo from Project Live, with a grant from the faculty here, and with Michael Rampe, we've been starting to develop some more of these 3D virtual I guess, components that we're going to build into a virtual reality experience. So there is another QR code here if you want to have a play around with this model online. So this is a video of it, but you can go in and you can move and zoom in and rotate, and have a look underneath. So yeah, so there's the web link, and there's the QR code for that. So the last thing is just to say thank you. And these are, obviously it takes a family to conduct this research and these projects, and just like to acknowledge all my collaborators throughout this work. And also just here's a link to the survey, for your friends and for family, obviously not for people in the audience that have just been through this talk. But yeah, it'd be great if anyone's happy to share this with friends and family, just to try and spread the word that we're looking for, or community groups, just to try and if you go to my Twitter page, then it's my pinned link on there, so you can also access it through that, and it's on my website as well. So yeah, please distribute if you can, to try and get some more opinions of the general public. And the very, very last thing is just to highlight that on International Women's Day next Monday, we will be hosting a Wikipedia Edge-a-thon. So what we're doing, it's a joint initiative between WOMEESA and the GSA to try and increase the number of Wikipedia pages for notable women in earth and environmental sciences. So you register via this link, and then we'll provide you with more information, and you can also get more information on the website. So thank you.